welcome to today's edition of Cracking the Cryptic, where as I'm recording this, it's another day of absolutely filthy weather here in the UK. I am recording this in the middle of a storm, and there may be flashes of lightning indeed. I don't know whether you'll see them. If they happen, I will see them because it's dark outside as I'm recording this. And yeah, well anyway, it's going to be a jolly frightening solve if so. But what are we going to be trying to do? We're doing a puzzle called The Secret of the Three Worlds by Playmaker6174. Now Playmaker6174 is an absolute doyen of the Discord server, one of the finest solvers in the world of Sudoku and one of the finest setters. And I think we've done other puzzles in this series. I don't really know what the secret of the three worlds is, but I think I've done something else of the three worlds by Playmaker before, and I think they might all be arrow Sudokus. Anyway, this one's been recommended to us several times. Apparently it is a very beautiful puzzle with an unusual and clever break-in. So it's quite rare that we actually get recommended puzzles just purely on the basis of the break-in, but today is such an occasion. And I'll read you the rules of this one, which are very straightforward in a moment. In fact, I don't have much news today, just an appeal really. If you enjoy the channel, please think about liking the video. We don't ask for that very often. Maybe subscribe to the channel even, that would be absolutely great. Or think about joining us if you're a real fan of Sudoku over on Patreon, where we have the best Sudoku club on earth going. Several thousand of you are members of that, and I don't blame you at all. It's a couple of bucks a month for all the bonus content that we put out over there. And with that, let's have a look at the rules of The Secret of the Three Worlds and see if we can find this break-in. The rules are as follows. Normal Sudoku rules apply. Digits along an arrow must sum to the digit in that arrow's circle, and that is it. So how do arrows work? Well, what we do is we sum up those two digits. So let's make that 3 and that 5. 3 plus 5 is equal to 8. So we'd have to put 8 into this circle, and then we'd have to make those two cells also add up to 8. And that's how it works, basically. Do have a go. The way to play is to click the link under the video. Don't know if you heard that thunder. But now I get to play. Let's get cracking. We've got this sort of antler head up here, haven't we, that looks... Well, I can see a modest deduction, which I will just mention about this circle. And that's based off the fact that these 4 digits all have to be different. So the minimum I could put into these 4 squares would be a 1, a 2, a 3 and a 4, and those digits sum to 10. Now this circle is effectively half the value of whatever we put into those 4 cells, because each of the if we view each arrow as x, obviously these cells are sort of 2x, and with x being the sum of the circle. So the minimum value for this is 5, being half of 10. But half, is it worth? It might be worth pencil marking. Why don't we do it? 5, 6, 7, 8, 9. Pencil Mark would fully approve of that and endorse it. In fact, he may and has been known occasionally to go up to 9 pencil marks in a cell, but I don't normally resort to that. Now, the same exact thing, actually, if we think about how just a rotation almost of this antler head here, those 4 digits have to be different, therefore they're a minimum of 10 in terms of their sum. Half of 10 is 5, so that's at least a 5. We get another heavily pencil marked cell. Right, that one is actually better, because that's 3 different digits, which is at least 1 plus 2 plus 3, which is at least 6. So that one is at least 6, which is higher than 5. There is a knowledge bomb for you from Cracking the Cryptic. And then we've got this funny scissory arrangement down here. What's that doing? I don't know. I don't think we can apply the 10 logic there. I mean, it's certainly true to say those 2 cells together have to add up to at least 10, because these will be 1, 2, 3 and 4 as a minimum. But in theory, one of them could be a 1-2 pair, couldn't it? The other could be a 3-4 pair, and then the one that was the 1-2 pair would only add up to 3. So I can't really... Oh, I see. Right, hang on. I think it's to do with these small, short, stubby arrows, though. Yeah, okay. Okay, so one of these arrows in this box, one of those cells, is that digit. Colouring might help me to show this. Let's just switch to some colours. Those two digits are the same. These two digits are the same. And that's oh, that's a terrible choice of colour. I apologise immediately. Let's try. That's better. The reason that you can see these are one cell arrows, so whatever's in this cell just reappears here. So this cell, whatever this is, let's make it purple. Can I see the... No, I can't. I can't really see the arrows against the... I'll try red. I can see the arrow against the red background. So this digit, which can't be yellow or blue, where does it go in this box? And the answer is it goes in one of those 4 cells. Now this is at least a 6. So now these circles are adding up to at least 12, I want to say, because imagine this was a 6. Then one of these cells is a 6, and the other 3 could be 1, 2, and 3. And that would add up to 12 altogether. So these still doesn't improve matters in terms of whether one of them could be as low as a 3. Because if one of them is a 3, the other could be a 9. And that might work. Alright, so what does that do? Yellow and blue have to be in those cells, so there's something going on there, look. Yes, alright, here is a tiny deduction. We can't make those 2 cells the yellow and the blue numbers, i.e. these 2 circles, because we've just worked out that those circles add up to at least 12. So if we put this as yellow and blue, that would be at least a 12 by mathematics. So in fact, right, I don't really know how to pencil mark this. This is definitely the value that's in one of these circles, and the other one is going to be on the arrow in one of these 2 cells. So let me just think about this. So if we did go for 3 and 9 into these cells, which is about the most extreme values that they could take, then we could put 3 on the arrow here. We could have 9 here. And then this circle wouldn't actually be under very much pressure at all. That's really weird. That's really weird. And it's so weird. I find myself looking at other bits of the grid to try and find some other deduction here. It's very odd though, because this part of the grid is sort of mutually exclusive. I can't see any natural interaction between these cells and sort of the rest of these columns 4, 5, and 6. I mean, there's simple deductions like this is not yellow or blue, but how can we actually get something good? Nah. Okay. The answer is I don't know. This offset circle and this offset circle don't look good either, because they're not sort of pointing at the same chute, are they? This one points into a different chute of digits. And by chute I mean, you know, I'm viewing those 3 cells together and these 3 cells together. The power with these is that they have an impact within their sort of 3-row segment. Right. So if this is... maybe we can rule out some digits from this. If that's a 6 and that's a 1, 2, 3, what are we saying then? We're saying that there's a 6 in one of these, and then the other 3 digits. Well, I was saying they could be 1, 2, 3 before, but that's actually wrong, isn't it? Oh, Right, that's lovely. Good grief. Okay. I don't know what this does yet, but I have spotted something here. Yeah. Okay. Right. Well, the thing I'm trying to think about is how many digits there are in common between those 4 cells and those 3 cells. So those are 7 different digits. But we know this one appears as one of those. I think it might be easier if I'm just going to allocate this red digit to one of these cells to show you what I mean. Let's just say it's there. It's not going to make any difference to the point I'm trying to make. Now the point I want to think about is this. Let me use grey for this because I want to clearly indicate. So you can see these 3 digits here. How many of those 3 digits can be grey? And the answer, or can be a digit that appears in grey. And the answer must be only 1, I think. Because if it was more than 1, if there were 2 grey digits in this 3-cell sequence, then you'd have to put 2 grey cells up here, along with blue and yellow, because we know that the grey digits are not the same as blue and yellow. So there would be, in other words, there would be 4 digits in those 3 cells. That's not going to work. So the maximum number of common digits between this string and this string is 1. Now, can you have 0 common digits? That strikes me as highly unlikely, because that would mean the minimum sum of the grey digits would be 21, because 1 plus 2 plus 3 plus 4 plus 5 plus 6 would be 21. So we'd have 21 for those cells plus that digit, which is at least a 6. So that's 27. Yeah, that doesn't work. Because if we're saying that those 3 circles add up to 27, they'd all have to be 9. And that most certainly is wrong. So we do need a repeated digit between these greys, and we can only have 1 repeated digit. So that means that the minimum sum of all these grey digits then is going to be 1 repeated digit. So if we make the different digits 1, 2, 3, 4 and 5, which is the lowest we can have, they would add up to 15, and then repeat a 1. That would be 16. That's 16. Oh, yeah, okay, no, all right, this is brilliant. It's head scratching, but it's brilliant. I've been trying to view those 3 digits as the sort of limiting factor, but in fact, because this cell comes in here, I can view all the greys, and these 3 obviously add up to red. So by working out that grey contains 5 different digits and 1 repeated digit, I'm effectively adding up those 2 cells in doing that. And so the minimum value of these cells is now those 5 digits plus the 1 repeated digit, which is 16. So this is a minimum of 7 and 9, but it could be 8 and 9, but it must have a 9 in it because those 2 digits must add up to at least 16. Hopefully I've made that clear. I think the only thing I think I elided over, because I didn't notice it, was that because I've worked out that these cells had to be 5 different digits and 1 repeat, I'd failed to take into the account that meant that because these 3 add up to this and this gets transported over here, so you can think of this if you like. One way of thinking about it might be that it includes those 3 greys. So this in effect could be represented mathematically as 6 grey digits, but only only, of those 6 grey digits, you could only repeat 1 digit. That's quite a nice way of looking at it, to think about this cell as being 3 little cells, being those 3, with only allowing 1 repeat within those 6 grey cells. So that's why we get to 16 here. And that must be good. That means one of those is a 9. Because one of these is a 9, one of those is, which means that's not a 9. Aha. Aha. Which means one of these is a 1. Well, the repeated digit doesn't have to be 1. It could be 2. Because we could have 1, 2, 3, 4, 5, and then a repeated 2, which would give us 17. So we don't know for sure that there's a 1 in here, but I suspect there will be. So the repeated digit is a 1 or a 2. So there's a 1 or a 2 up here, along with... Oh, that's beautiful. Oh, good grief. Right. Well, I've done it. This is 17. Sorry, this is 7 and 9. It's not 17. It's definitely not 17. Right, let's come back to these cells. Because these include the repeated digit, and they include a 9. Well, I can't put 9 on an arrow without making this at least 10. So the 9 must go there, because by Sudoku, there's a 9 in... We know that there's a blue and a yellow digit in this string, so that's got to go here. And then there's a 7 or an 8 on this arrow. Well, if there was an 8 on this arrow, this would be a 9 as well. It would repeat. So there must be a 7 on this arrow, along with a 1, allowing this to add up to 8, QED. So there we've done it. This has got to be 7, 9. That's got to be 7, 9. I see why people like this break-in. It's just brilliant. That is now not a 7. So this is 6 or 8. We know the repeated digit is a 1 now because it's this digit. So there's got to be a 1 in that string. Now I've got to be careful here because that red was a float. I don't know which one of these is red. One of them is, but I don't know it's this one. Okay. Well, alright, and I do sort of know the value of these digits now, don't I? Well, I know the value of all of them that are not the red one, because I know it's 1, 2, 3, 4, 5, and a repeated 1. So I don't quite know how to... I'm going to pencil mark it like that, but one of these is red, and that complicates matters. And that because the red one is a 6 or an 8. Okay, I was suddenly thinking, okay, it can't be 6 because then I couldn't put 6 in here. But it can be 6 because one of these is red and that would be the 6. Right, that's weird. That is very, very strange. Okay. Oh, right, no, it's simpler than I'm making it. It's Sudoku, isn't it? 8 in this box goes where? And the answer is I don't know, but it's definitely in one of those 3 cells, which means in this box, we know 8 is not in a circle. 8 is on an arrow. And if 8's on an arrow, that must be a 1, 8 arrow adding up to 9. Now that doesn't mean we know which one of these arrows is a 1, 8 arrow adding up to 9, but it does mean that this is an 8, because the only high digit we're allowed down here, the only digit we're allowed that's not a 1, 2, 3, 4 and 5 is the digit that's in here, and we've just worked out there's an 8 down here, so that must be the digit that's in there. So that's an 8. There's a 1, 8 pair here adding up to 9. Oh no, I do know where, sorry, of course I can just use this again. So this is not the 1, 8 pair, which means that this is the 1, 8 pair, which means that is the 9, which means this is the 9, this is the 7, this is the 7, this is a 1 by Sudoku. Good grief, it's all just coming now. This is, okay, this is either 2, 5 or 3, 4. This doesn't involve a 1. And these are different, aren't they? Yeah, okay, so let's have a quick think about that. Because remember there was only 1 repeat between these 7 cells. And that repeat is the 1. Whatever's here is not here. And yet both of these dominoes add to 7. So they are different. Right, what we could do now is change our colouring then. This domino, I want to make it very clear. Oh, that's a terrible choice of colour. I can't see these arrows against the backdrop. I'll make this one grey. I'll make this one... No, I still can't see the orange. Can I get rid of the blue and the yellow now? Yeah. I'm going to risk that, I think, as an alternative strategy. So now I'll just make that yellow to indicate it's different from this. Okay, so now in this box, right, yeah, I see. In this box, where does 6 go? The answer is in one of those cells. And that means that's a 6 by Sudoku. What, not a 9, a 6, Simon. So this is right, and that's lovely, because now that's yellow. Because by Sudoku it's not grey, so those two digits are yellow. So there's some yellow down here along with a 6, I see. So this is 6 and yellow. Let's put the 6 in there. And these two cells are the grey cells that have to appear in this row. So this is 6 and grey. That's not 9 anymore by our old friend Sudoku. And now... Right, 9 in box 5 can't go on an arrow, look. So 9's in one of those two positions. Which is probably important for some reason. Come on, Simon. Use your brain. What's going on? We could argue that... Okay, we can do... Now I can... Oh, hang on. Right, I've seen exactly what this does now. And this is quite gorgeous. It is quite gorgeous. It's this red 8. Now, how does that red 8 affect box 4? Watch this. Well, it's not in those cells. Can you put red 8 on its own arrow? Not unless you accompany it with a 0. That won't work. Can you put red 8 on this arrow? No, because then that's going to be a 9, and it doesn't seem to be allowed to be. So red 8 goes into these cells, knocking itself out of here. Now, as I was looking at the 7, 9 a moment or two ago, I was wondering about where 7 went in this box, and I was noting that the annoying thing was it could go on an arrow, because this could be an 8, but now it can't be an 8. So now I'm going to come back to that question and ask where 7 goes in this box. And you can see that now it can't go on an arrow, and therefore it is worthy of pencil markage. So that becomes 7, 9. That's now not even a 7. So this is 5 and 6 dominoes, which means they've got to have... What does that mean? Well, if this is 5, this is a 2-3 pair and a 1-4 pair. And if this is 6, this is a 2-4 pair and a 1-5 pair. So I think we could perhaps pencil mark that like this. And Mark would fully approve of this, but there are some digits that are definitely in this quadruple, aren't they? It must have 1, it must have 2. Does it have to have 3? No, it doesn't have to have 3. If that's 6, it doesn't have to have 3. So 1s and 2s are common to the somewhere in those 4 cells in this box. Now the 1s align with the ones in box 8, so the 1 in column 4 is now not there, not here, so it's in one of those cells, which is probably not surprising. 6 is not in any of those cells, so there's a 6 in one of these cells in box 5, so that's not a 6 anymore. 8. Yes, where does 8 go in this box now? Well, given this pencil marked 8, it's in one of those two positions. Okay. So what's that then? Ah, okay. So perhaps what I'm meant to do now is to think about that set of digits as a sort of quadruple. Because these circles do see each other. So again, maybe it's this 10 logic again. Those 4 digits have to add up to at least 10. But that is a 5 or a 6 only, so it's not higher than 6. So this cannot be lower than 4. If it was 4, that would have to be 6. But if this was 3, there would be no possible way of making those 2 cells enough to cater for the fact that those 2 dominoes there must add up to at least 10. So that digit... Oh, no, I can do better than that. Right, this is really lovely actually. Playmaker 6174, this is seriously beautiful, this whole puzzle. This bottom bit was a bit head scratchy, but it's beautiful. This bit with the 8s, 7s and 9s is beautiful, and this is beautiful because I've realised this can't be a 4. Because although I ruled out 3 from these dominoes, what about 4? If that's 5, one of these dominoes is a 1-4 pair. If that's 6, one of these dominoes is a 2-4 pair. So this cannot be 4. So it has to be at least 5, and that means it's forming a pair with this one. Must be, because it can't be 7, 8 or 9. So that's a 5, 6 pair, which means these 4 cells add up to 11 by maths, which means they are 1, 2, 3 and 5, which means that one's not got 4 on it. So this is a 1, 2, 3, 5. It's the only way of making 11 in 4 cells. And you can't make that one 5. Because if you make that one 5, you can't put 5 anywhere in this string. If that's 5, you can't put 5 on its own arrow, because it would be accompanied with 0, and those can't be 5. So that's 6. This is 5. There's now no 5 on any of those cells. That's the takeaway from this. The only way of making this now add up to 5 is if it's a 2-3 pair. So this has got to be a 1-5 pair. And if this is a 2-3 pair, what's this one? It's a 1-4 pair. And now those squares are now known. They are 8 and the 5 that we've just managed to knock off these cells. Now that 1-5 sees that cell, so that's an 8, that's a 5. I love this. This is just superb. Now those squares are a 1, 2, 3, 4 quadruple with a 1 up here. So this is a 2, 3 or a 4. This is an 8 arrow that is not 1, 7 or 3, 5. So that's 2, 6 and I can just fill it in, which is a rare treat. 6 and 2 go into the grid. So where do we put 7 and 9 in this box now? And the answer is into one of 2 cells. So, whoopsie, that's a 7-9 pair. So now I know those digits. They've got to be 3, 4 and 8 by Sudoku, which means I know those 2 are a 1-2 pair. Now I've got 1s aligning in these dominoes. So we ask where 1 goes in column 7. It can't go in any of those 6 cells. So it's in one of these. Now can you put it here? No, because then it would get reflected there and bash into itself. So the 1 is in one of those 2 positions. Well, okay. That's probably not. That's probably okay, isn't it? Right, where does 6 go in this box now? 6 can't go there because it would get reflected and hit itself. We mustn't have digits hitting themselves, so that's a 6. So there's a 6 in one of those 3 cells. That cell is, I want to say 2, 3, 4 or 5, but probably I can get rid of, yeah, this has become a naked single. So this cell itself is down to 2, 3, 4 or 5. It reflects here where it sees 5. In fact, it sees 5 in 2 positions. It sees 4 in the 1-4 pair. It sees 2 over there. So it's only left with the ability to be 3. So those are 3. That gives me a 3 and a 2 here. It means that's not 3. But I think more interesting is how this 7 arrow is made up, which is now not 3, 4. So yellow is now 2, 5, which is beautiful. Good grief. So this is now 3, 4. Grey is 3, 4 over there, which is done. It's just all falling. It's all falling. This 2, 5 means that's become a 4. So there's no 4 up here. We get a 1, 2, 3 triple at the top, which is presumably going to put some sort of pressure on these arrows. But let me just see. Can I do 2? Yes, I can. 2, 5. So that's not able to be 5 anymore. 6, 7, 8, or 9. That digit. Can we do something with it? I don't think I can actually. Okay, all right. Let's try these cells. That's a 5, so that's got to be 5. That's got to be 1. That's not able to be 8. Look, so look, hang on. This column has got interesting things. It's got a pair there and a 7, 9 pair there. So those squares seem to have to be 2, 5, and 6, which is actually not very helpful because we don't know anything about rows 1, 2, and 3 yet. So that's underwhelmed, hasn't it? Okay, perhaps. Well, I'm going to pencil mark these cells in the interests of being diligent. So 2, 5, and 6 into those, with that one not allowing itself to be 5. And is there some sort of restriction? I'm just wondering, because these circles see between them quite a lot of numbers, don't they? This can't be 1. It can't be 2 because this one sees 2. It can't be 3 or 4 or 5. Can it be 6? Maybe. It seems to have a 6 here. Can I rule 6 out of this cell? If that's a 6, that will be a 6. That will be a 6. I don't think I can. What about 7? Bar humbug. No, I can't. Okay, so I can see 9 is seeing that cell. I can't actually see any higher digits seeing that, so perhaps it's 6, 7, and 8 into those particular positions. Oh dear. Okay. Right, we're going to have to think again. Right, I can place 8 in this box by our old friend Sudoku again, raising its head. So one of these cells is an 8. Can I put 8 there, really? Can that be 9? Maybe it can, actually. Right, okay. Alright, let's try that digit, because I can see that can't be 6, 7, or 9. This digit is at least a 4. So this cell is at least a 5. So 4 plus 1 would still give us 5. 5, 6, 7, it's this cell. Right, that's got to be an 8. It's the only high digit left, and that's actually mighty, look. Because that's getting rid of 8 from there, which means this now is only able to be 6 or 7. This can't be 8. Which... okay. That feels like it's doing something profound. I just can't see what it is. How does that work? Well, all right, let's do that. I've got a 6, 7, 9 triple in column 6. I was trying to do it a snazzy way, but I can't see any way of doing it snazzily. So this cell is 1, 4, or 8 by Sudoku, and it's not 1 because of this 1, 4, 8 triple. So that's now not 6. So 6 is in one of these two cells. Now, if that's 6, that becomes 6, that becomes 6. If that's 6, what can we say about anything? Those two become 7. And that becomes a 7, which looks reasonable. Right. Okay. This column is interesting, I think, because I have not put 1, 3 and 4 into it. Yeah, that's interesting. And the 1 has to be at the top. And if the 1 has to be in one of those two cells, and the 1 in box 3 is in one of those two cells, then where does 1 go in this row? And the answer is not there, and not there, and not here, and it's not here because of the pencil mark 1, so that is a 1, which is potentially quite cool, because now both of these arrows have sort of got a little bit... Well, this can't be 4, 1 anymore. In fact, we can pencil mark this. This is 5 or 6, isn't it? Oh, that's forced. C6. So the only way of making this add up is with a 5. That's probably been available for ages. But anyway, we'll take it. Now, what does that mean? This digit can't be 7 now, because that would have to be a 5. Can that be 9? That would have to be a 7. So that's either 7 or 4. I don't know. Okay, where does 8 go in this column then? Because it can't go here, and it doesn't seem to be able to go anywhere else. So, oh right, so one way to think about that is where does 8 go in this box? It seems to only be allowed to go there, which makes that an 8. That seems to indicate that's a 1, based off our pencil marking, which means that's a 1. Right, so this can't be 9, because that would require an 8 here, so that's got to be 6, which is sort of not what I was expecting. That's a 4, that's a 4, that's a 1, that's a 1, that's an 8, that's a 7, that's a 7, therefore that's a 7, that's a 7, that's a 9, that's a 9 in the middle of box 2, this is a 5 by maths, that's a 5 by Sudoku. This column needs 2 and 6, so that's got to be the 6. That's the 2. That's the 6. That's using that 2 there. And we might be on the home stretch. That's a 3, so that's a 4. That's a 3. That's an 8. That's a 3. That's a 4. Now we need, what do we need? 4 and 9. Okay, we can do that. 9 and 4. 4's in one of those cells, not resolved. Oh, come on, this must be resolved now. That's not got 5 in it. That's not got 6 in it. That's not got 5 in it. So that's the 5. These two squares are a 2, 3 pair. The 3 must go there. The 2, the 1, the 7. So this column needs a 4 and a 9. So that's got to be the 4. That's got to be the 9. The 9 and the 7 drop into place. That's a 4 by Sudoku. That's a something by Sudoku. Can't scan it in time. That's a 7. This is 2. This is 6. So that's probably 6. And that's probably 9 in the corner. That is just gorgeous, isn't it? Yeah, it is. It is. The answer to that question is yes. What an absolutely sensationally good arrow Sudoku. I mean, you think you've seen everything. I don't know how many arrow Sudokus I've done in my life, but it is a lot. It is a lot. And we have our Arrow Sudoku app, for which I designed some puzzles as well. And that, you know, so I've even made some puzzles, and I would love to have been able to set something this clever. This is just really, really gorgeous. It's got several little stages to it, and they all work just beautifully together. And they sort of make you just think, gosh, it's sort of deity-given talent that Playmaker 6174 has. So, loved it. Let me know in the comments how you got on. I do enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.